This is my machine, and for some reason, it's learning. What's up, Code Squad? If you're new here, welcome to the squad, and if not, welcome back. My name is Kylie Ying, and today I'm going to be talking about machine learning. More specifically, we'll dive into supervised learning, and then we'll learn how to use TensorFlow to create a neural net, and then use a neural net for some text classification. Sound exciting? Let's get started. All right, jumping straight into things, the first thing that we're going to do is go to colab.research.google.com, and it'll pull up a page like this. You're going to click New Notebook. This is going to create a new notebook, and let's retitle this to freeCodeCamp tutorial. Okay, it doesn't really matter, what you actually rename it to, as long as you have a notebook open, and just in case, you have some future notebooks, that's why you want to rename all of them. So the typical libraries that I'll import when I usually start a computer data science project are NumPy, so import NumPy as NP, pandas, import pandas as PD, and then import matplotlib. Okay, so because I'm going to be using TensorFlow in this video, I'm also going to import TensorFlow as TF, and then import TensorFlow hub as hub. Okay, now if you click Shift Enter, it'll run this cell. Another thing that you can do is click this little play button over here. That will also run the cell. So, cool. Yeah, if we click that, that runs the cell as well. All right, so the first thing that we're gonna need to do before we can actually do any data analysis is upload a data file. So this little folder over here, this is where we manage our data, this is where we manage our files. And I'm just gonna drag and drop the CSV file, the link is in the description below, into here. So click OK. And you'll see that this is currently being uploaded. Sweet. Might take a while because this is a pretty big data set. We can wait until this yellow thing goes all the way around. All right, so pause. All right, sweet. Now winereviews.csv has uploaded to this folder, which means that we have access to it in this notebook now. So now what we can actually do is import that CSV file as a data frame using pandas, which is this library here that we imported. So what I'm going to do is say df equals pd.readCSV. So this is just a command that lets us read a CSV file. And I'm going to type in winereviews.csv, and then also I'm going to use certain columns. So if we actually took a look at this data frame here, we can call df.head. We see that we have this unnamed column over here that contains a bunch of indices, and we don't really want that. So what I'm going to do is say use columns and give a list of the columns that I want. So I want maybe the country, the description, the points, the price, and I don't really care about some of these things like the Twitter handle. I think the variety might be cool to check out. Maybe the winery. All right, so let's run that and then now take another look at the data set. So now in our data set, we have the country, the description, the points, the price, the variety, and the winery. Something that I think would be really cool is to see if we can try to guess or ballpark, whether something falls on the lower end of the point spectrum or the higher end of the point spectrum, given the description that we have here. So the first thing that we do see also is that we have a few none type values in our data frame. That's what this here stands for. It means there's no value recorded there. So let's just focus on these two columns, actually, the description and the points, because I think that's what we'll try to like a line. We're going to use a description to predict the points. Something that we can do is a command called drop na. Don't know if that's, the right way to say it, but in my head, that's what I say. And we can say subset, which means that, in a subset of these columns, that's where we're going to try to drop the NaN column. So here I'm going to say description and then points. Run that. Okay, so don't even know if this has changed. Okay, I mean, we still see this because we didn't drop anything in that column because it doesn't really matter to us. Let's just quickly see, let's plot like the points column to see the distribution of the points. So we can use matplotlib for that. So let's do plt.hist. So this is going to be a histogram which shows the distribution of values because it's only a one-dimensional variable. So let's do df.points, which calls like this points column. And let's just say bins equals 20. Now, if we do plt.show, this should display our plot. All right. I didn't include the title and the axes because this is kind of just for us to quickly look at it. If you were to actually plot, this as some sort, if you wanted to actually plot this for other people to view, you might want to say plt.title is, points histogram, and the plt.label, the y label, so that label for the y-axis would be, n, the number of values that lie in each bin. And then the x label, I would say it would be the points. So if we see something like this, ta-da, there is our plot. This is our distribution of points. So we see that it seems like it's on a range from 80 to 100, which means that let's try to classify these reviews as below 90 and then above 90. So we're splitting this into two different categories: low, which is over here, and high, which is over here. Now, before we proceed with the rest of this tutorial, we're going to learn a little bit about machine learning because you can't really just dive into the code without understanding what's going on, or at least having, a vague sense of what's going on, which is what I'm going to try to teach in this video. So let's hop over to some more theoretical aspects of machine learning. So first, let's talk about what is machine learning. Well, machine learning is a subdomain of computer science that focuses on algorithms which help a computer learn from data without explicit programming. For example, let's say I had a bunch of sports articles and a bunch of recipes. Explicit programming would be if I told the computer, hey, look for these specific words such as goal or player or ball in this text. And if it has any of those words, then it's a sports article. On the other hand, if it has flour, sugar, oil, eggs, then it's a recipe. That would be explicit programming. But in machine learning, what the goal is, I instead provide the computer with some sort of algorithm for the computer to be able to decide for itself, hey, these are words associated with the sports article, and these are words associated with a recipe. Sound cool? It is, so stay tuned. Now, these days, we've heard a lot of words kind of, being thrown out there, such as artificial intelligence, machine learning, data science, cloud, blockchain, crypto, etc., etc., etc. Now, we won't talk about the cloud or crypto or blockchain, but let's kind of talk about AI versus ML versus data science and what the difference between all of these is. So, artificial intelligence is an area of computer science where the goal is to actually enable computers and machines to perform human-like tasks and to simulate human behavior. Now, machine learning is a subset of AI that tries to solve a specific problem and make predictions using data. Now, data science is a field that actually attempts to find patterns and draw insights from the data. And data scientists might actually use some sort of machine learning techniques while they're doing this. And the kind of common theme is that all of these overlap a little bit, and all of them might use machine learning. So we'll be focusing on machine learning. There are a few different types of machine learning. So the first one is supervised learning, which uses labeled inputs, meaning that the input has a corresponding output label to train models and to learn outputs. So for example, let's say I have these pictures of some animals. So we have a cat, a dog, and a lizard. Well, in supervised learning, we would also have access to these labels. So we would know that this picture is associated with a cat, this picture is associated with a dog, and this picture is associated with a lizard. And now because we have all of these input-output pairings, we can stick this data into a model and hope that the model is able to then generalize to other future pictures of cats or dogs or lizards and correctly classify them. Now there's also such thing as unsupervised learning, and in this case it uses unlabeled data in order to learn certain patterns that might be hiding inside the data. So let's go back to our pictures of our animals. And now we might have multiple pictures of cats, multiple pictures of dogs, multiple pictures of lizards. And also just a quick note that we would also have these in supervised learning, but all of these would have the cat label, the dog label, and the lizard label associated with them. But, okay, now going back to supervised learning, we have all of these pictures, and what our algorithm is going to want to do, it wants to learn, hey, these are all something, of group A because they're all similar in some way. These are all group B, and these are all group C. And it basically tries to learn this inherent structure or pattern within the things that, we're feeding it. Finally, there's reinforcement learning. So in reinforcement learning, there's an agent that's learning in an interactive environment, and it's learning based off of rewards and penalties. So let's think about a pet, for example. And every single time our pet does something that we want it to, so for example, some sort of trick, we give it a treat, such as in this picture. Now, if our pet does something that we don't want it to, for example, pee on our flowers, then we might scold the pet, and the pet would then start learning, okay, it's good when I do this trick and it's bad when I pee on the flowers. This is kind of what reinforcement learning is, except instead of your pet, it's a computer, or I guess an agent that's being simulated by your computer. Now, in this specific video, we're just going to be focusing on supervised learning. So that's using these labeled input and output pairings in order to make future predictions. Okay, so let's talk about supervised learning. So this is kind of what our machine learning model is. We have a series of inputs that we're feeding into some model, and then this model is generating some sort of output or prediction. And the coolest part is that this model, we as programmers are not really telling this model any specifics. We're not explicitly programming anything. Rather, this model, our computer, is trying to learn patterns amongst, this input data in order to come up with this prediction. So a list of inputs, such as the ones here, this is what we call a feature vector. We'll talk about that in some more detail later. So let's quickly talk about the different types of features or inputs that we might be able to feed our model. So the first type is qualitative data, and this means it's categorical, which means that there are finite numbers of categories or groups. So one common example is actually gender. And I know that this might seem a little bit outdated, but please bear with me because I just want to get the point of a qualitative feature across. So here in this picture, we see that there is a girl and a boy. So let's take these two different groups. First, you might notice that there's not exactly a number associated with being a girl or being a boy. So that's the nature of qualitative data. If it doesn't have some sort of number associated with it, it's probably qualitative. Now let's take a look over here. There's different types of flags. Like maybe these represent, your nationality might be a qualitative feature. Qualitative features don't have to necessarily be exclusive, but they just don't have a number associated with it, and they belong in groups. So you might have US, you might have Canada, you might have Mexico, etc., etc. These two specific qualitative features are known as nominal data. In other words, they don't have any inherent ordering in it. Now, our computers don't really understand like labels or English too well, right? Our computers are really, really good at understanding numbers. So how in the world do we convey this in numbers? Well, we use something called one-hot encoding. So suppose we have, a vector that represents these 4 different nationalities: USA, India, Canada, and France. What we're going to do is we're going to mark it with a 1 if that category applies to you, and 0 if it doesn't. So for somebody who has US nationality, your vector might look like 1, 0, 0, 0. For India, it might be 0, 1, 0, 0, Canada 0, 0, 1, 0, and France 0, 0, 0, 1. So that's one-hot encoding. It turns these different groups into a vector and I guess switches on that category with a 1 if that category applies, and 0 if it doesn't. Now, there are also other types of qualitative features. So something like age, even though a number might be associated with it, if we take different groupings of age, so for example, baby, kid, Gen Z, young adult, boomer, etc., etc. If we take these different categories, then this actually becomes a qualitative data set, because you can assign one of these categories to somebody and it doesn't necessarily map to a specific number. Another example of categorical data might be a rating system of bad to good. And this is what we call ordinal data. So even though it's qualitative, it has some sort of inherent ordering to it. So hence the name ordinal data. Now, in order to encode this into numbers, we might just use a system like 1, 2, 3, 4, 5. Quick note, the reason why we use one-hot encoding for our nationalities, but we can use 1, 2, 3, 4, 5 for ordinal data, is because let's think about things this way. Our computer knows that 2 is closer to 1 than 5, right? And in a case like this, it makes sense because 2 is slightly less worse than 1, whereas 5 is actually really good. So of course 2 should be closer to 1 than 5. But if we go back to our nationality example, it doesn't really make sense to say, to rate USA 1, India 2, Canada 3, and France 4. Because we could also switch around these labels and they would still be distinct groups. And they're just different. It's not like one of them is closer to the other than something else. They're just different. I mean, I guess it depends on the context, but if we're talking nationality, they're just different, right? So you can't necessarily say 2, which I think I assigned to India, is closer to 1, USA, than France, which is 4. Like, a computer would think that, but just thinking about it logically, that wouldn't really make sense. So that's the real difference between these two types of qualitative data sets, is how you want to encode them for your computer. When we're talking about features, we also have quantitative features. And quantitative features are numerical valued inputs. And so this could be discrete and it could also be continuous. So for example, if I wanted to measure the size of my desk, that would be a quantitative variable. If I wanted to tell how hot, what the temperature of this fire was, that's also another quantitative variable. Another type of and these two are both continuous variables. Now, let's say that I'm hunting for Easter eggs, and this is how many Easter eggs I collect in my basket. It probably doesn't make too much sense to say, I have 7.5, but rather I have 7. That would make sense. Or 8. Somebody else might have 2, which means that I won. But, aside from that, this is something that would be a discrete quantitative variable, because we do have, it's not continuous, right? There are discrete values, integers, positive integers, that would be able to describe this data set. Over here, this is continuous, and over here, this is discrete. Those features, those are the different types of inputs that we might be able to feed into our model. What about the different types of predictions that we can actually make with the model? So there are a few different tasks that, we have in supervised learning. So there's classification, which means that we're predicting discrete classes. For example, let's say we have a bunch of pictures of food. So, here we have a hot dog, we have a pizza, and we have an ice cream cone. An example of classification might be, okay, well, this gets mapped to a hot dog label, and this gets mapped to pizza, and this gets mapped to ice cream. And if we have any additional photos of one of these, we want to map them to one of these 3 classes. This is known as multi-class classification because we have a bunch of different classes that we're trying to map it to. So hence the name multi-class. Now, what if instead of hot dog, pizza, and ice cream, we had another model that just told us whether or not something was a hot dog? So this over here is a hot dog, and these over here are simply not hot dogs. Well, this is known as binary classification because there's only 2, hence binary.
It's ready.
Please, God.
What would you say if I told you there is an app on the market?
We're past that part. Just demo it.
Okay. Let's start with a hot dog.
Holy shit.
Yes!
It works.
Oh, motherfuck!
Huzzah!
Jin Yang, my beautiful little Asiatic friend, I'm going to buy you the palapa of your life. We will have 12 posts, braided palm leaves. You'll never feel exposed again.
I'm gonna be rich. Fuck you, Guilfoyle. Do pizza.
Let's do pizza.
Yeah.
Okay. Pizza.
Not hot dog?
Wait, what the fuck?
Eh?
That's it? It only does hot dogs?
No, and a not hot dog.
Now, let's talk about some other examples of classification to kind of really drill this down for you. Other types of binary classification might be positive or negative. So if we have restaurant reviews, positive or negative, 2 different categories. Something else might be pictures of cats versus pictures of dogs. Cool, cats and dogs. And then maybe we have a bunch of emails and we're trying to create a spam filter. Another example of binary classification might be spam or not spam. Now, what about multi-class classification? So going back to our first example of the cats and dogs, well, we also had a lizard. You might also have a dolphin. So different types of animals. That might be something that falls under multi-class classification. Another example might be different types of fruits. So orange, apple, and pear. Another example might be different types of plant species. But here, basically, you have different types of classes and you have multiple of them, more than 2. All right, there's also something known as regression. And in regression, what we're trying to do is predict continuous values. So one example of regression might be, this is the price of Ethereum and we want to predict what the price will be at tomorrow. Well, there are so many different values that we can predict for that, and they don't necessarily fall under classes. Like classes just doesn't intuitively make sense. Instead, it's just a number, right? It's a continuous number. So that's an example of regression. Or it might be, what is the temperature going to be tomorrow? That's another example of regression. Might be, what is the value of this house given, how many stories it has, how many garages it has, what is its zip code, etc., etc. Okay, so now that we've talked about our inputs, now that we've talked about our inputs, and now that we've talked about our outputs, that's pretty much, machine learning in a nutshell, except for the model. So let's talk about the model. Okay, so before I dive into specifics about a model, let's briefly discuss how do we actually make this model learn and how can we tell whether or not it's actually learning. We'll actually use this data set in a real example, but here let's just briefly talk about what this represents. So this data set comes from a certain group of people, and this outcome is whether or not they have diabetes. And now all these other numbers over here, these are metrics of, how many pregnancies they've had, what their glucose numbers are like, what their blood pressure is like, and so on. So we can see that all of these are actually quantitative variables. They might be discrete or they might be continuous, but they are quantitative variables. Okay, so each row in this data set represents a different sample in the data. So in other words, each row represents one person in our data set. Now each column is a different feature that we can feed into our data set. And by feature, I literally just mean like the different columns. So this one here is blood pressure. This one here is number of pregnancies. This one here is insulin numbers, and so on. Except for this one over here. This one is actually the output label that we want our model to be able to recognize. Now, these values that we actually plug into the model, again, this is what we would call our feature vector. And this is the target for that feature vector. So this is the output that we're trying to predict. This over here, this is known as the features matrix, which we call big X. And all these outcomes together, we call this the labels or the targets vector, Y. Let's kind of abstract this to a piece of chocolate or a chocolate bar like this. And, we have all the numbers that represent our X matrix over here. And the values are outputs, Y, our targets, over here. Now, each of these features, so this is our feature vector, we're plugging this into the model. The model is making some sort of prediction, and then we're actually comparing this to our target in our data set. And then whatever difference here, we use that for training. Because, hey, if we're really far off, we can tell our model and be like, hey, can you make this closer? And if we're really close, then we tell our model, hey, keep doing that. That's really good. Okay, so this is our entire bar of chocolate. So let's say this bar here represents all the data that we have access to. Do we want to feed this entire thing into our model and use that to train our model? I mean, you might think, okay, the more data, the better, right? Like if I'm trying to look for a restaurant, I'd rather have 1,000 reviews than 10. But when we're building a model, we don't want to use all of our data. In fact, we want to split up our data because we want some sort of metric to see how our model will generalize. So we split up our chocolate bar into the training data set, the validation data set, and the testing data set. Our training data set is what we're going to feed into our model, and this might give us an output. We check it against the real output, and we find something called the loss, which we'll talk about in a second. But you can think of the loss as a measure of how far off we are. So how far off are we? Put that into a number value and then feed that back into the model. And that's where we're making adjustments. This process is called training. Now we also have this validation set. So this validation set, we also feed into the model, and then we can actually assess the loss on this validation set because, again, we have the real answer and we have this prediction, and we can see how far off we are. But this validation set is actually used as kind of more of a reality check during or after the training to ensure that our model can handle unseen data. Because remember, up until this point, our model is only being trained with our training set data. Okay, so for example, if I have a bunch of different models and all of these are my validation data sets and these are the predictions, well, okay, this loss over here is kind of high. This one's a little bit closer, but look, this one is the lowest. We want to actually decrease the difference between our prediction and our true target. And so another use case for the validation data set is to actually say, okay, well, model C seems to perform the best on unseen data, so let's take model C. Now, once we've selected model C, then we can actually go back and use our test set, which again is unseen data. And we plug that into model C, see how it performs, and then we can use that metric compared to, our targets as the final reported performance. This test set is used to kind of check how generalizable the final model is. Okay, so I kind of touched on, something called a loss function, but what exactly does that mean, and how do we quantify how different things are? Well, this would probably give us a higher loss than this, right? Like we would want that too, because it's a little bit further off. And something like that should be a lot further off, which means that our loss function, the value output from the loss function, should be a lot higher than the previous two that we just saw. Okay, so there are a few different types of loss functions. So let's put our mindset in terms of regression for a second. So we're trying to predict a value that's on a continuous scale. So this might be the temperature tomorrow, right? Now, if we have a bunch of different cities that we're trying to predict, then we have a bunch of different points, right? So this here, y real, this is the actual value that we found in our data set, and y predicted, this is a value that our model has output. So what we're trying to do is we're trying to find the difference between these two values and then use the absolute value of that and then add all of these up, for every single point in our data set, so all the different cities, in order to calculate the loss. So in other words, what we're doing is we're literally just comparing, hey, for every single city, how different is our predicted value and the real value, and then sum up all of those values. So as you can see, this is basically just an absolute value function. So that's what L1 loss is. Now, if we're really close, if our predictions are really good, then you can see how this loss becomes really small. And if our values are really far off, well, that becomes pretty large, right? There's also another type of loss called L2 loss, which is the same idea, but instead of using the absolute value function, we square everything. So this is also known as mean squared error, which you might have heard of. Basically, here, instead of summing up all the differences, we actually square all the differences and then we sum those up. So again, this is what a quadratic formula looks like. So this is what the squares would look like. And again, as you can see, if we're only off by a tiny bit, our loss is really small, which means that it's good. And if we're off by a lot, then our loss gets really, really big, really fast. Okay, now let's think about the classification mindset when we're trying to predict, let's say, just two different classes, so binary classification. Well, your output is actually a probability value, which is associated with how likely it is to be of class A. So if it's closer to 1, then class A seems to be more likely. And if it's closer to 0, then it's probably class B. So in binary cross-entropy loss, what happens is you're taking the real value times the log of the predicted value, and then adding that with 1 minus the real value times the log of 1 minus the predicted value. Summing that up and using a normalization factor. You don't really have to know this too well. This is a little bit, more involved mathematically, but you just need to know that loss decreases as the performance gets better. So one of the metrics of performance that we can talk about in classification specifically is accuracy. So let's say that we have a bunch of pictures here and we want to predict their labels. So here I also have the actual value. So of course this is an apple, this is an orange, apple, apple, etc. And use your imagination. Think that, these two are slightly different from the original. Well, let's say that our model is predicting apple, orange, orange, apple. So, we got this right, we got this right, we got this wrong, and we got this right. So the accuracy of this model is 3 out of 4, or 75%. If you just think about it in English, that makes sense, right? Like how accurate our model is how many predictions it correctly classifies. Up until now, we've talked about what goes into our model, the features, what comes out of our model, what type of prediction it is, whether we're doing classification or regression, but we haven't really talked about the model itself. So let's start talking about the model. And that brings me to neural nets. Okay, so the reason why I'm going to cover neural nets is because they're very popular and they can also be used for classification and regression. Now, something that I do have to mention though is that neural nets have become sometimes a little bit too popular and they are being sometimes maybe overused. There are a lot of cases where you don't need to use a neural net. And if you do use a neural net, it's kind of like using a sledgehammer to crack an egg. It's a little bit, too much. There are plenty of other models that can also do classification and regression. And sometimes the simpler the model, the better. And the reason for that is because you don't want something that's so good at predicting your training data set that it's not good at generalizing. And often the thing with neural nets is that they are very much a black box. The people who create the neural nets don't really know what's going on inside the network itself. When you look at some of these other models, when you look at other types of models in machine learning, oftentimes those might be a little bit more transparent than a neural net. With a neural net, you just have this network with a ton of parameters, and sometimes you can't really explain why certain parameters are higher than others. And so the whole question behind why is a little bit lacking sometimes. But with that being said, let that be your warning. We're going to talk about neural nets anyways because they are a great tool for classification and for regression. All right, let's get started. So as I mentioned, there are a ton of different machine learning models. This one here is called a random forest. This one here could just be classic linear regression. This one is called a support vector machine. And these different types of models, they have their pros and cons. But we're going to be talking about neural networks. And this is kind of what a neural net looks like. Actually, this is exactly what a neural net looks like. You have your inputs, they go towards some layer of neurons, and then you have some sort of output. But let's take a closer look at one of these neurons and see exactly what's going on. Okay, so as I just mentioned, you have all of your inputs. These are our features. Remember how we talked about feature vectors? So this would be a feature vector with n different features. Now, each of these values, remember, because our computer really likes values, each of these values is multiplied by a weight. So that's the first thing that happens. You multiply your input by some weight. And then all of these weights go into a neuron. And this neuron basically just sums up all these weights times the input values. And then you add a little bias to it. So this is just some number that you add in addition to the sum product of all of these. And then the output of the sum of all of these plus the bias goes into an activation function. And an activation function, we'll dive into that a little bit later, but you can think of it as just some function that will take this output and alter it a little bit before we pass it on. And it could be the output, but this is the output of a single neuron over here. Okay, and then once you have a bunch of these neurons all together, they form a neural network, which kind of looks something like this. This is just a cool picture that I found on Wikipedia. All right, so let's take a step backwards and talk about this activation function because I just kind of glossed over it and I didn't really tell you exactly what it is. So this is another example of a neural net. This is what a neural net would look like. You have your inputs, okay? They go into these layers, and then you have another layer, and then you have your output layer. So the reason why we have a non-linear activation function is because if the output of all of these are linear, then the input, into this would also just be a sum of some weights plus bias. what we could do is essentially propagate these weights into here, and this entire network would just be a linear regression. I'm not going to do the math here because, it involves a little bit of some algebra, but if that's something that you're interested in proving, it would be a really good exercise to prove that if we don't have a nonlinear activation function, then a neural network just becomes a linear function, which is bad. Like that's what we're trying to avoid with the neural net. Otherwise, we would literally just use a linear function. Ta-da! Without activation functions, this becomes a linear model. Okay, so these are the kinds of activation functions that I'm talking about. There are more than these, but these are 3 very common ones. So here, this is a sigmoid activation function. So it goes from 0 to 1. Tanch, which goes from -1 to 1. And then ReLU, which is probably one of the most popular ones. But basically what happens here is if a value is greater than 0, then it's just that value. And if it's less than 0, then it becomes 0. So basically what happens in your neural net is after each neuron calculates a value, it gets altered by one of these functions. So it basically gets projected into a 0 or a 1, a -1 or a 1. And then in this case, 0 or whatever the output is. And then it goes on to the next neuron and on and on and on until you finally reach the output. So that's the point of an activation function. When you put it at the very end of a neuron, it makes the output of the neuron non-linear. And this actually allows the training to happen. We'll talk about that also in a second. We've seen this picture before, how we have the training set that goes into our model, and then we calculate some loss, and then we make an adjustment, which is called training. So let's talk about this training process now. Okay, so this is what our L2 loss function looks like, if you can recall from a few minutes ago. Basically, it's a quadratic function, and when your real and predicted values are further apart, then the difference becomes, the square of the difference becomes very large, right? And when they're close together, then you minimize your loss and all is good in the world. Okay, up here, the error is really large. And we want to decrease the loss, right? Like the smaller the loss, the better our model is performing in some ways. Like loss is just a metric to assess how well our model is performing. So our goal is to get somewhere down here. And now up here, this is the part that might involve a little bit of calculus understanding, but because not everybody out there knows calculus, I'm going to skip the numbers and just use diagrams. So if we're up here, this is the opposite of the slope, right? Like the slope here, I mean, it's increasing. It would be positive, but we want to take, if we want to get down here, we want to go in the opposite direction as that. The higher up we go, the more steep we want to step, right? Because the further away we are from our goal, whereas maybe down here, we want to take a baby step over here. Because we don't want to overshoot. We don't want to, pass this and never be able to find it. So we use something called gradient descent in this case. And gradient descent is basically it's measuring to some extent the slope at a given point, and it's taking a step in the direction that will help us. This is where backpropagation comes in. And backpropagation is the reason why neural nets work. So if we take a look at this L2 loss function, okay, you might think, yeah, like this depends on what our Y values are, right? Like what is our predicted value and what is our real value? Okay, well, our real value is staying the same. Our predicted value is a function of all the weights that we just talked about and all the inputs, right? But our inputs are also kind of staying the same. So as we adjust the weight values, then we are actually altering this loss function to some extent, which means that we can calculate the gradient, the slope of our loss function with respect to the weights. Okay, got that. So if we're looking at the various weights in our diagram, we might calculate a slope that's with respect to that weight. and each of them might be a slightly different value, as we can see here. So what we're going to do with gradient descent / backpropagation is we're actually going to set a new weight for that parameter, and that value is going to be the old weight plus some alpha. We'll get back to that, but just think of this as some variable multiplied by this value going down this way. A quick side note, if you're studying machine learning some more, this might be a minus sign and this would be the gradient. But for all purposes right now, because we're using these arrows instead, it's more intuitive to just add something in this direction. If that confused you, you can ignore it until you start getting into the math of backpropagation. But what I'm trying to say is that essentially calculating this gradient with respect to one of the weights in the neural network allows us to take a step in that direction in order to create a new weight. And this value alpha here, this is called our learning rate, because we don't want to take this massive step every single time, because then we're making a huge change to our neural network. Instead, we want to take baby steps. And if every single baby step is telling us to go in one direction, then okay, fine, we're going in that direction. But taking small steps is better than, overshooting and diverging off into the land of infinities. Yeah. You can think of this as, for example, if you were tailoring something, it's better to remove like bits and bits of the fabric rather than removing an entire chunk and realizing, oh my gosh, I just took off way too much. So that's what the learning rate is for. It's so that we don't, take off a huge chunk of the fabric. Instead, we go bit by bit by bit. Okay, so then going back to all these other weights, we can see how each weight in the neural net is getting updated with respect to what this gradient value is telling us. So basically, this is how training happens in a neural net. We calculate out the loss. Okay, we see there's a massive loss. We can calculate the gradient of that loss function with respect to each of the weight parameters in the neural network. And now this allows us to have some direction, some measure of the direction that we want to travel in for that weight, whether we want to increase the weight or decrease the weight. We know based on this gradient that, we're finding. So that is how backpropagation works, and that's exactly what's happening in this step right here. That is our crash course on neural networks. It is not the most comprehensive crash course out there. If you are interested in neural networks, I do recommend diving in deeper into the mathematics of it, which I'm not going to cover in this class because not everybody has had the mathematical prerequisites. But again, if that's something you're interested, definitely go and check it out. Let's move on to talk about how we would actually implement this neural net in code if we wanted to create a neural net. So this is where machine learning libraries come in. Okay, so in machine learning, we often need to implement a model. We probably always need to implement a model. And if we want our model to be a neural net like this, okay, that's great. We could go and we could code, each neuron, or we could code a neuron class and we could stitch them all together. But we don't really want to start from scratch. That would be a lot of work when we could be using that time to fine-tune our network itself. So instead, we want to use libraries that have already been developed and optimized to help us train these models. So if we use a library called TensorFlow, then our neural net could look something just like this. And that's a lot easier than trying to go through and, develop and optimize the network entirely from scratch ourselves. So straight from the website, TensorFlow is an open source library that helps you develop and train ML models. Okay, great. That sounds like exactly what we want. So TensorFlow is a library that's comprised of many modules that, you might be able to see here. But for example, we might have this data module. And here, we have a bunch of tools that help us import data and keep data consistent and usable with the models that we will create. Another great part of this API is Keras. So here we actually have a bunch of the different modules which will help us, create models, help us optimize them. And these are different types of optimizers, etc. So basically, the whole point of this is that, we want to use these packages. We want to use these libraries because they help us maximize our efficiency where we can focus on training our models. And they're also just, really good and like fine-tuned already. So why would we want to waste our time to code stuff from scratch? All right, so now let's move over to our notebook and I'm going to show you guys how to actually implement a neural net using TensorFlow. Just, a straightforward, feed-forward, no pun intended, neural network. Now that we've learned a little bit about neural nets, about TensorFlow, let's try to actually implement a neural net using TensorFlow. So let me go back to this Colab tab and let's actually create a new notebook. Okay, and this notebook, again, I'm going to call this maybe just a feed-forward neural net example. All right, now I'm going to, again, use these same imports, run this. Great. It's running. Okay, so now the second thing that I'm going to have to import in here is my data set. And so here I have a data set called diabetes.csv, which is also in the description below. Click OK there. And that was a substantially smaller data set than the one that we tried to import at the beginning, which don't worry, we will get back to at the very end of this video, but that's why it took significantly shorter to upload. All right, so this data set that we're using here in diabetes.csv, this is a data set that was originally from the National Institute of Diabetes and Digestive and Kidney Diseases. And in this data set, all of these patients are females at least 21 years old of Pima Indian heritage. And this data set has a bunch of different features, but the final feature is whether or not the patient has diabetes. Okay, let's take a look at this data set. So the first thing that we can do is, once again, create a data frame. So we're going to use read CSV again, and here we can just say diabetes.csv. Let's see what this looks like. All right, so we can see that each of these is one patient and how many pregnancies they've had, their glucose, blood pressure, skin thickness, etc., a bunch of other measurements. Okay, so it's always a good idea to do some sort of data visualization on these values in order to see if any of these, have some sort of correlation to the outcome. And there are many different metrics that you can run. You can try to literally find the correlation between pregnancies and the outcome. But for this purpose, I think it's a lot easier to visualize things in, I guess, a visual way. How else would you visualize things? So here, what I'm going to do is I'm going to plot each of these as a histogram, so each value in the feature as a histogram, and then compare it to the outcome. So let's try to do that using a for loop. So for I in range, and here I'm going to use the columns of the data frame up until the very last one because that's the outcome. That's the one that we're actually comparing against. What I'm going to do is say the label is equal to dataframe.columns I, and actually let me make this screen larger for you guys because I know that some people, okay, hopefully you can see this a little bit better. So anyways, down here for I in this range, okay, how about this? This is better. Okay, so for each, basically this for loop here is trying to run through all of these columns except for the last one. And the label is basically just getting the data frame column at that index. So to show you guys what that actually looks like, let's run df.columns. So again, this is just, it's similar to going through a list of these items. Okay, so the label, we're, indexing into something in this list, and what we're going to do is plot the histogram. So we can index into a data frame by calling the data frame and then saying, where the data frame outcome is equal to 1, which means that they do have diabetes. And then, so this basically creates another, let me show you. This basically is a data frame where all the outcomes are equal to 1. Okay, cool. So this is our new data frame where all the outcomes are 1, which means that all of these patients are diabetes positive. And then we're just going to index into the label that we have right here. So we're just indexing into the column. And what I'm actually going to do is the same thing now, but instead of 1, make this 0. So now this here, let me show this to you guys again. This here is a data frame where all the outcomes are 0. So that means that everybody here is, diabetes negative. Okay, perfect. Well, we want to tell the difference between the two. So I'm also going to assign these colors. So here, let's use blue and red. And then, of course, a label. So this is no diabetes. And this up here, diabetes. All right. So PLT. Now let's give this a title. Let's just use, the name of the label. And then the Y label is N. And the X label is the label. If we call plt.legend like this, then this actually shows us the legend including these labels. And at the very end, we call plt.show in order to see the plot. So let's run this. All right. Basically, for each of the values, we are plotting the measurements here. And it's kind of hard to see, diabetes versus no diabetes. So another trick that we can do here is we can say alpha equals 0.7. If we run these again, you'll see that it makes them a little bit easier to see behind one another. Okay, so something else that we might want, if we take a look at the number of values, so if we say the length of this versus the length of this, so this is saying how many patients are diabetes positive and how many are diabetes negative, we see that we actually have two different values. One of them is only 268 positive patients and then 500 negative patients. So what we actually want to do is normalize this, which means that we want to compare these histogram distributions to how many actual values there are in that data set. Otherwise, you can clearly see that there are more no diabetes patients here than diabetes patients, and this isn't really a fair measurement. So I'm going to say density here equals true. And just for kicks, I'm going to say the number of bins that we're going to use in our histogram is 15. Then here we would say this is probability because we're normalizing now using the density, which means basically that we're just taking each of these values and dividing it by how many total values there are in the data set. So instead it's a ratio for each column rather than just a straightforward number. Okay, click enter again. And now here we have more of a visualization. So it does seem like, people who have diabetes might have more pregnancies, or people, higher glucose levels. That makes sense, right? Seems like maybe slightly higher blood pressure, but that's pretty inconclusive. Maybe skin thickness a little bit, but also, insulin a little bit inconclusive. It does seem like perhaps people who have diabetes have a slightly higher BMI, but so on. So you can see that there's these values aren't separable, which means that we can't really tell based on one value whether or not somebody has diabetes or not. And this is where the power of machine learning comes into play, is that we can actually learn whether or not, or predict whether or not somebody has diabetes or not based on all of these features altogether. Okay. So now that we have this, what we're going to do is split this into our x and y values. So recall that the x is a matrix, right? So here I'm going to say it's just going to be all the columns up until the last value, dot values. So let's run that and let's see, oops. And what does this give us? This gives us now an array. This is now a NumPy array. Okay, and we're going to do the same thing with y. Except y is just a single column, so we can do this. And I missed the S again. Okay, so if we see y, it's a huge array, but it's one-dimensional, as you can see, and it's just all the different labels in the data set. So now we have our x and our y values. We can actually just go ahead and split this up into our test and our training and our test data sets. So something that I'm going to import is from sklearn. So this function here allows us to split arrays or matrices into random train and test subsets, which, is very useful. So all we have to do is plug in our arrays and it should help us, we would dictate the test size and the train size, and then it would help us split them up. So what I'm going to do is say x train and x, I'm going to call this temp, y train and y temp equal, we have to import this. So actually I'm going to come back up here and say from sklearn.model selection import this. Okay, so make sure you rerun that cell, but now we have access to that function. So here train test split, and I'm going to pass in my x and my y arrays, and then I'm going to say the test size is equal to, let's use 60% of our data for training and 20% for validation and 20% for tests. So what I'm going to do first is just split this up into 0.4, and I'm just going to pass in random state equals 0. So this allows us to get the same split every single time. Now the reason why I want to do this again, but use 0.5, is now with this temporary data set, which is technically, the test set, we're going to split this now into the validation and the test. So let's do xValid, test. And instead of x and y, we're going to pass in the temp that we just created up here. So this is essentially x and y, but only 40% of that data set. And now we're breaking this down further into 50-50, which is going to be our test, our validation and test data sets. So let's run this. Cool. Checks out. And let's build our model. So here I'm going to say model equals TF, which is TensorFlow, dot keras, which is part of TensorFlow. That helps us write, some neural nets and stuff like that. Called TF dot keras. So let's check that out. Okay, TF keras. So basically it's this API that allows us to easily build some neural net models. And here we're going to call the sequential. So let's see, sequential. Basically, it groups a linear stack of layers into a model, which is exactly what we want because our neural net is exactly a stack of layers. So let's pass in some layers here. Okay, I think how I'm going to architect this is I'm just going to use a very simple model. So keras.layers.dense 16. Okay, so basically what this, actually, let me, activation equals ReLU. Okay, what this is like setting up here is this is a layer of dense neural nets. What does dense mean? It just means that it takes input from everything and it outputs a value. But densely connected is just, okay, it's a layer that's deeply connected with its preceding layer. So it just means that every single neuron here is receiving input from every single neuron that it sees from the past. All right, going back to here, this just means that this is a layer of 16 neurons that are densely connected. So if we go back to here, it means that this layer here is comprised of 16 different neurons. And then our activation function is ReLU, which is one of the activation functions that we saw previously, where if x is less than 0, then this becomes 0. I guess less than or equal to 0, this becomes 0. And if x is greater than 0, then this becomes just x. Okay. And I'm just going to add another layer in there just for kicks. And then finally, we're going to conclude this with a layer of only one node. But instead, this layer is only going to have one node, and the activation here is going to be sigmoid. And what that helps us do is this is where the binary classification comes in, because sigmoid, if you can remember, maps to 0 or 1. So the point of this activation function is that it maps our input to a probability of whether or not, something belongs to a single class. So this is our neural net. It was really that easy. We can click enter or shift enter, and then now let's compile this model. So we can call model.compile, and we're going to need a few different things here. So the first one is going to be our optimizer. So you can see here that there are a bunch of different optimizers that TensorFlow already has for us. Now, which one do you choose? That's a hard question to answer, because it's a question that people still don't really know the answer to. But one of the most commonly used optimizers is Atom, so that's where we're going to start. So going back to our example here, let's do optimizer, and let's set this equal to TensorFlow.keras.optimizers.atom, and we're going to set our hyperparameter called the learning rate. Let's start off with what the default is, so 0.001. Now, the second thing that we have to do is define our loss function. So our loss is equal to tf.keras.losses. So now, because we're doing binary classification, the one that we're going to use is called binary cross entropy. So binary cross entropy like this. And then the final thing that we're going to do is add a metric for accuracy. And the reason why we're doing that is because we want to know, how many do we actually get right? So enter. We now have a compiled model. We have a neural net that we can actually feed data to and we can train. But before we do that, let's actually see how well this might perform on, our training data and our validation data. What we're going to call is model.evaluate. And here, let's pass in xtrain and ytrain and see what happens. Okay, so here we're getting a loss of 16 and an accuracy of 0.35, which is around 35%. So that's pretty bad. What about, instead of train, let's do validation. Okay, it's around the same, a loss of 11 and accuracy of 35%. All right, this is because our model hasn't seen our train or validation set yet, and that's why the accuracy is so low. We haven't really done any training. So let's see if we can fix that. What we're going to do is call model.fit and pass in the xtrain and the ytrain values. Pass in something called the batch size. And then epochs is how many iterations through the entire data set we're going to train this. And pass in the validation data. Now, this validation data is just so that after every single epoch, we can measure what the validation loss and the validation accuracy is. So X valid, Y valid. Now we can run that. All right, so you can see that our neural net is training. Now going back really quickly to this batch size. Batch size is just a term that refers to the number of like samples or training examples. In this case, it's the number of women that we have like samples from that is used in every single iteration. So this is how many samples we see before we go back and we make a weights update. So you can see that here, look, our loss in our training set is decreasing fairly successfully. And our accuracy, okay, our accuracy seems to be increasing. Great. Now, what about our validation loss? Okay, our validation loss seems to be decreasing. A little bit of an increase at the end, but that's a good sign. And our validation accuracy seems to be also increasing. Well, let's see if we can do better. So, a few problems with our current data set. We see that, look, all of our values here, I mean, our insulin range is from 0 all the way out to like 800. Whereas something else might be on the scale of like, you know, skin thickness is on the scale of 0 to 100, but BMI is on the scale of 0 to like 2.5. The fact that our features are so different in terms of their range, that is something that could be messing up our results. So instead, what we're going to do is we're actually going to scale the results. So all of them are on a more standardized range. The first thing that I'm going to do is I'm going to import a package that lets us scale. So just like how we imported this function up here, I'm going to import from sklearn preprocessing. I'm going to import standard scaler. Okay, let's rerun this again. And let's go back down to down here, like before we split it up into the train and test sets. Okay, so here, let's just run this again for good measure. But instead of splitting it up right here, what I'm going to do is I'm going to scale the quantities. So here I can define a scalar and set this equal to standard scalar. And I'm going to say, okay, this scalar, let's fit and then transform this X matrix. All right. So once we've done that, our new data, so let's actually see what X looks like now. So we can see that everything is a lot closer in range. It goes, you know, from maybe around like 1 to like -1. Okay, let's actually see, let's plot these values again and see what exactly is going on here. So here, let's transform this back into a data frame. So what I can do is say transformed data frame equals pandas.dataframe. So this is creating a data frame. And then here, okay, let's use a placeholder called data. And then the columns are the same as our current columns. Now, this data, we're actually going to do something called a horizontal stack, which means that we're taking our X, our new transformed variable X, along with this Y, but we have to do a little bit of reshaping here. So we're going to call numpy.reshape because right now our X is a 2-dimensional matrix, but Y is only a 1-dimensional matrix, which means that, let me just show you real fast. So x.shape, if we see what this is and then compare this to y.shape, see, this is a 2-dimensional variable and this is only 1-dimensional. It doesn't have a 1 here, which means that it's not, you know, a 768 by 1 matrix. It's just a vector of length 768. And if we call a horizontal stack of the two, there's going to be an error. So instead, we're going to reshape this. And this just means, okay, project it into something where -1 means like numpy gets to decide. This one just means in that second dimension, it'll be comma 1. So here it's going to return an object of 768, comma 1. All right, so let's run this. Oops, here, columns. Cool. And then instead of data frame dot columns, actually all of these we can leave the same, but here we just want to make sure that we're plotting the transformed data frame. So if we can see now, like most of these, so what standard scalar is doing is it's actually mapping our values to a normal distribution and trying to calculate like how far off our values are from the norm. So here, you know, we can see that glucose levels now range, I mean, it looks like it's fairly centered around 0 or -1. But all of these are now normalized. Okay, so we can actually delete the cell now that we've visualized it. We don't need it. And what we're going to do is we are going to, this is now our new x. And we can directly pass that down into here. But one other thing that I had mentioned is, remember how if we take x and we say x for the outcome is equal to 1, or sorry, I shouldn't say x, I should say the data frame, or the transformed data frame, doesn't matter. And then if I set this equal to 0, remember how these two, sorry, little typo. Remember how these two values are so different? Like the number of non-diabetes patients is almost double the number of diabetes positive patients. So this can sometimes also lead to the neural net not training so well. Instead, what we're going to do is we're actually going to try to get these two to be approximately equal. And we can do that with another thing called random oversampler, which means that we're essentially trying to get like more random samples into that first sample so that they now balance out. These two values balance out, the lengths. Now, okay, we can do this by importing another package. So we're going to use a package called imbalanceLearn.oversampling. And we're going to import random oversampler. Now watch what happens. Oh. Okay, that did not give me an error, but in the past this might give you an error, and if it does, what you're going to do is just come up here and type in an exclamation mark, pip install -u imbalanced-learn. Run that, and then this, if there's an error here that says, you know, there's no library, then this up here will solve that for you. And yeah, you would have to restart the runtime, but because this worked, I'm not going to do that. All right, let's come back down here. So right before we're splitting it into the test and train sets, over here, let's actually use this random oversampler in order to get both of these equal to 1. So here, let's call random oversampler. And then let's split x and y. Well, I guess let's redo this x and y definition by calling fit resample and then x comma y. Then we run this cell. All right. We can't exactly, we never like reran. We can do this again. All right, so now we see that we have 500 where the outcome is 1 and 500 where the outcome is 0. So this is a good sign. This means that now our data set is balanced in terms of the outcomes. Let's rerun all of these. Okay, so it seems like our accuracy is closer to 50% now. And let's think about like intuitively why that's happening. Well, okay, let's say that the first result, it's just predicting random numbers 0, 1, 0, 1, 0, 1, okay? But our data set naturally, before, it had more values that were negative than positive. And so naturally that accuracy would be skewed towards something closer to 30% if, for example, it's like a 1-to-2 ratio, just because of the fact that we didn't have very many values that were diabetes positive. But now because we've balanced it, this value is much closer to 50. All right, now let's try to train our model once again. Okay, so we see that, again, this loss is decreasing. This is good. And our accuracy seems to be increasing, which is also good. And let's check our validation, because remember, we need to see how this would generalize to unseen data. Our validation loss, great, seems to be decreasing. Validation accuracy seems to be increasing. And now our validation accuracy is somewhere closer to 77%, which is a significant improvement. All right, now at the very, very end, what we're going to do is we're going to evaluate this model on our test data set. And we can see that, okay, our loss is around 0.5, but that doesn't really mean anything to us. But our accuracy is around 77.5%, which is pretty good because we've never seen this data before. So that's a quick tutorial on how we just use TensorFlow to create a neural net and then use that neural net to predict whether or not the sample of Pima Indian descent women have diabetes or not, based on, some data that we were given. So that's very, very cool. Now, for the other tutorial that we started off with, we will get to that in 1 second. But first, I wanted to talk about some more advanced neural network architectures. Let's talk about recurrent neural networks. We've already seen the feedforward neural net. We've already, done an example problem with it. We're very familiar with it, right? You have your inputs and then they feed into, the hidden layers and then you get your outputs. Okay, cool. Yeah, we've got that. You guys have got that. But what if this data over here, our inputs, were some sort of series or sequence? So, for example, they might be stock prices from the past 20 days, or they might be values that represent different words in a sentence where the sentence has some sort of, sequence to it. Or it might be temperatures from the past 10 months, so on. Like you get what I mean. Like, just basically if this was some sort of sequence. If this data were a sequence, a feed-forward neural net would not do a really good job at picking that up. Why? Because all of these different layers, it evaluates each value as if they were independent. So even if there were a series, it's a lot harder for a feed-forward neural net to pick up on that. That's where recurrent neural networks come in. So basically here we have our data points, and this is our data point taken at T0, at T1, at T2. So we're going through time. And what we can do is we can feed these into a layer of weights. And then these layer of weights may or may not produce some sort of output. But basically what this is doing, because the calculation at each point takes into account the previous calculations as we move through this network, we're essentially creating some sort of memory with the neural net. So this neural net, whenever, when we feed in x2, so x at t2, we actually have some information that we remember about x at t0 and x at t1. So that makes a recurrent neural net very powerful. Ta-da! This part acts as a memory. And now instead of just straightforward backprop, we have to use something called backpropagation through time in order to adjust these weights. Okay, this is our unfolded RNN, and this is what our folded version would look like. So you see how, our x at time t is just fed into this neuron, which outputs some value at time t, and this value kind of gets cycled into the next iteration of x, and so on. Well, there are a few problems, right, with this, because this RNN, if you imagine there are many, many time steps, this might end up being a really deep network. And then two, during backpropagation, we might be seeing this same terms, like the weights in here, over and over and over because of the recurrent nature of this RNN. Now, why are those problems? Well, these two kind of compound on each other, and you might get something called exploding gradients, where the model can become really unstable and then incapable of learning because all the gradients that we're using in backpropagation are getting bigger and bigger and bigger until they reach like infinity. And then, you know, our model updates become literally all over the place, and we can't really control our weights, and then, yeah, not good stuff happens. On the other hand, there's also such thing as vanishing gradients. So here, our gradients get closer and closer and closer to zero, and so at this point, our model stops updating, and then it becomes also incapable of learning. So some really smart people have studied these problems, and they've decided, okay, here are some different ways that we can overcome this problem. There are a few things that you can do with the activation function, but I'll let you look that up on your own time. Instead, I'm going to talk about different sorts of cells or neurons that people have come up with in order to combat this. So there's such thing as the gated recurrent unit. And this unit, as you can see, so it still takes x at time t as an input, but here it just has a bunch of gates that are associated with it. And then it has some sort of output. So there's just more parameters inside the neuron itself rather than trying to just directly sum up some weights. There's also the long short-term memory unit, which looks something like this. It's very, very similar to the unit that we just saw, but instead of 2 gates, it has 3. Again, I'm not going to dive too deep into these things because these are more advanced topics, but I just wanted you guys to be aware that these exist. And if we do use them in an example, this is exactly what's going on. It's just we have a few more, bells and whistles inside of our neuron. All right, so now that we've touched upon some of the more theoretical aspects of neural nets and machine learning, let's walk through a different TensorFlow example with text classification and try to see if we can classify some wine reviews. So let's get started on that. Let's go back to our Colab notebook where we were studying the wine reviews, and let's continue on with that. So here I have that notebook open. This is the code that we typed at the very beginning of this class. So here we have our wine reviews, and we actually need to restart. We need to rerun some cells, and we need to re-import our data. So let me do that over here. Okay, so we see that it's imported. Let's rerun everything. All right. Cool. Okay, these are our points. This is what we're trying to classify. Now let's split this up into a low tier and a high tier, as we were saying earlier. So how we can do that is if we type in quality label, let's say. So let's come up with a new label. Or actually, let's just say this is the label. And we say this will be if df.points. So basically the points column of the data frame, if it's greater than or equal to 90, this basically will return a Boolean. So either every single row, it will be false if it's less than 90 or true if it's greater than 90. And all I'm going to do at the very end here is force this as a type for an integer so that it gets mapped to 0 or 1. Because remember, our computer understands numbers really well. So here, then I'm going to say that the data frame, I don't need all the columns. I know which ones I'm going to use, so I'm just going to say it'll be the description and the label. So remember, this is the description and this is the label. Okay, and you know what? Let me just add points in here anyways. So now if I look at the very beginning of this, okay, so we have the points and we have the label. Let's look at the tail. Maybe that'll be, okay, so here again we have the points, they're equal to 90, and then the label. All right, great. So let's now split this up into the training, validation, and test data sets. So I wanted to this there just to show you guys that, we were mapping this to the right thing, but this is what we can actually keep. Now that we have our data frame, I want to split this up into our training, validation, and test data frames. Now, we did this in a slightly different way before, but I'm going to show you a different way to do it because I want you to realize that there's not just one way to do it. Like whenever you're working with a data set, you want to be able to be flexible and split things up in different ways. So here, I'm going to say train val test, and I'm going to set this equal to np, so numpy.split, which is going to split our data frame. And this is the data frame that we're going to split. And actually what I'm going to do is I'm going to mix things up a little bit. So I'm going to say sample, and I'm going to sample all of them, which is going to basically draw random samples, but sampling the entire data frame. And then I'm going to pass in the different cuts where I actually want there to be breaks in the data frame. So what that's going to look like is I want it to be 60% for the training, 20% for the validation, 20% for the test. And actually in a data frame this size, you could even go like 80% for training, 10% for validation, 10% for test. And the reason is just because there's so much data that like even with your validation and test sets, even if you're using only 10%, that's still enough data to kind of see how it generalizes. So actually that's what I'm going to do. So I'm going to map this to an integer, and I'm going to say, okay, so 0.8 will be our first cut, meaning 80% will go towards the train data set. So I'm going to say 0.8 times the length of this data frame. And then our second cut is going to be at the 90% mark, which means that 10% of the data set will be for the validation here, and 10%, the remaining 10% will be for test. So if we run that, okay, cool. And we can quickly say, like, you know, let's print the length of these. Great. So you can see still plenty of samples for our validation and test data sets. All right, so this next function I'm actually going to copy from this TensorFlow module right here. All right, so we're going to use this. We're going to slightly edit it. And basically what this function does is it converts each training, validation, and test set data frame into a tf.data.dataset object, and then it will shuffle and batch the data. So let's copy this code and go back to ours right here. Now I'm going to make a slight difference. Because our data set is so big, I'm actually going to change this to a larger batch size. And then down here, instead of using batch size, I'm going to do tf.data.autotune. Okay, great. So let's run this, except actually, so in this data set, I believe they use target to define their target column. Okay, yeah, so they use target to create their target variable. But for us, we already have a column that defines it, and we've called it the label. So instead, what we're going to do is we're going to change this to label. Okay, and then the next thing that we're going to do is instead of this part here with all of this, we're just going to set the data frame equal to data.description, because that's the only part of the data frame that we actually care about. Alrighty. And here we can, because we changed that, we can remove this. And if we run that, this should be able to successfully create our train data, our validation data, and our test data. So here I can do train data equals df to dataset, and I'm going to run this on the train data. And actually, let's just copy and paste this a few more times. And here, instead of train, this will be valid. And here I will call this test. And actually we didn't create a valid, it's val. Now run this, hopefully great, there are no errors. So basically what this function is doing, it's shuffling our data for us, and it's formatting it in a proper, format, but then it's also batching it into our batch size that we specified and prefetching. Now this prefetch, you can kind of, I guess you can think about it as just trying to speed things up a little bit, trying to optimize things a little bit. So it just reduces some friction. So these are our data sets. Now let's try to take a look at like what's actually in here. So something that we can do is called train data of 0, but actually this train data is now going to be like a TensorFlow dataset. So what you need to do is you actually need to convert it quickly so that we can see what's going on. So you'll see that this is actually a tensor. I guess it's a tuple in this case, but you have the tensor of all the strings, and then you also have the corresponding labels that are associated with them, the zeros and ones that we came up with. All right. Great. So let's talk about how our model is now going to work. One thing that we imported that you might have noticed up here was this TensorFlow hub. So what TensorFlow hub is TensorFlow hub is a repository of trained machine learning models. So basically these are models that are ready to use. They just need some fine tuning, and we can actually use one of these to help us in our process of text classification. So recall that computers don't really understand text that well, right? Like computers understand numbers really well. So we actually need a way to transform all of these sentences like this into like numbers that our computer can understand. And that's where this embedding comes into play. So one embedding that we will actually use is this NNLM, this EN English, and then dimension 50. So this is token-based text embedding trained on English Google News using like a 7 billion document corpus. So it's a saved model that they already have for text embedding. And let's see how we do. So you can say embedding equals, set that, and actually, you know what, let's just label this. Okay, so here is our embedding. Then we're going to create a variable called hub layer and set this equal to hub.keras layer. And this is, you want to pass in the embedding link. And the data type that we're actually going to use, we're going to tell this that we're using strings. And then finally, we are going to tell this that, you know, trainable is true. Okay, cool. Oops. We can actually call this hub layer, and we can do that by passing in, let's do this little hack again, train data, and just say 0. Oops. Okay, so basically what we did, we need to only pass in the strings. So basically what we've done here is every single sentence that we had in our data set, we're essentially projecting it into a length of 50 vector containing only numbers. So that's what our embedding did. It basically transformed our text into this vector of numbers that now our model can go and understand. So let's build our model. So let's, again, call keras sequential. So previously what we did was we passed in, a list of all the different layers, but I'm just going to show you guys another way that you can build a model. So here you can also do model.add. And the first thing that we're going to add is this hub layer that we defined up here. So basically now the first transformation will be this text to value, numerical value transformation. Then what I'm going to do is I'm going to add a layer. And this is just going to be a classic dense layer. And let's use 16 neurons again. And we're going to use ReLU. And I'm just going to add another layer of those. And then finally, I'm going to add my final output, just like in the previous neural net that we created in our feedforward neural net. Okay, so now that we have our model, I'm going to actually compile it with the same exact compilation statement as the previous model, the feedforward network that we did. So let me just paste that in here. So I'm saying model.compile. I'm using Atom as the optimizer again. And actually the slowing rate, let's go back to 0.001. I had copied that from another example. And then for the loss, we're again going to use binary cross entropy. And for our metric, we're going to add accuracy. Now these are because we're doing binary classification. Okay, so here first, let's actually, so now that we have our model and it's compiled, let's try to evaluate the untrained model on the trained data. And let's actually do the same thing for the validation data. Okay, so it seems like our accuracy is around 40%, not so great. Our loss maybe around 0.7. Okay, so let's see what will happen if we do model.fit. So here, let's pass in our trained data, and let's do 10 epochs, and let's pass in our validation data. Okay. Now we're starting to train. Okay, so our accuracy is increasing. It's over 50% now. This is a good sign, and our loss seems to be decreasing. So this means that our model is training. Cool, it's still increasing. We like to see it. And it's still going. Okay, so I'm gonna let you guys train your model. You can pause the video really quickly, but I'll be back once our models are done training. Okay, so our model's finished training. Let's take a look at the results. So here it seems like our loss is steadily decreasing, which is a good sign. And our accuracy seems to be increasing almost to 90%. Okay, that's also a really good sign. Now, if we go over here and look at the validation loss and the accuracy, our validation loss, okay, it starts pretty high and then it decreases and then it seems like it starts to go back up again, which means that it seems like as training's going on, the validation performance is actually worse and worse. And if we look at the accuracy, okay, it starts off pretty decent at 80% and it gets better and then it starts to kind of plateau and then it dips a little bit. Okay, so what's going on here? This is a classic example of overfitting. So overfitting means that the training data that you do see, that your model sees, the model learns how to predict the training data really well, but then it generalizes really poorly. So what we can actually do is we can plot the model history. So if we do history.history, oh, what happened? And we look at the accuracy. And then we also do the validation accuracy. Okay, just some labels here. What we can, all right, and then let's just give this a title. And then some labeling. What is going on here? And then at the very end, we can do plt.show. So this is going to plot our accuracy, hopefully. Oh, I think we have to type out accuracy. Okay, so we can see that our training accuracy starts here and it gets better and better and better, whereas our validation accuracy seems to, okay, it does well and then it kind of tapers off. Now, if we look at the loss, it's a different story. So here, let's just change this plot a little bit. And let's look at this again. Okay, so it looks like our training loss actually decreases very well, whereas our validation loss seems to decrease and then start to go up again. So basically, our model is incapable of generalizing because we've trained it so much on our data that we're feeding it. So how do we fix this? One way would be to add something called dropout. And dropout just means that every once in a while you select a few nodes that aren't really working. So if I do this, I can add a few layers like this in here, and that should actually improve my training. So the reason why this works is that every single time the model has to basically go through these obstacles, these dropout layers, where some nodes aren't working and try to figure out how to work around that. So that helps it generalize a little bit. We're just adding a little bit of randomness in there. All right, so here let's repeat our hub layer, compile our model, evaluate. Okay, it seems like this is already really high, but that's fine. It could just be the opposite of what we just did. All right, and then also another thing to do is stop earlier. So let's just use 5 epochs. All right, I'll see you guys after training. All right, so we're back. Let's take a look at our results. So our loss is decreasing, accuracy increasing, great. Okay, so our loss seems to increase a tiny bit by the end, and our accuracy seems to decrease a tiny bit by the end. But this is probably a much better generalizable model than our previous one that we had trained. So finally, what we can do is we can evaluate this on our test data in order to get our final results. So sweet, look at that. Our loss seems to be around 0.38 and our accuracy is around 83%. So that seems to be really good. Awesome. All right, so up until this point, we just created a neural network that we saw would help us with text classification. However, we did use part of the TensorFlow hub, which, is not a bad thing. But if we wanted more control over this model, what would we have to do? And so I'm just going to show you guys really quickly how we would recreate this model using a LSTM. Here, I'm going to label this section LSTM. And the first thing that we're going to do is to create some sort of encoder for our text, because once again, our computer does not understand English. So what I'm going to do is create an encoder and set this equal to tf.keras.layers.text vectorization. And then here I'm going to say the max tokens. Well, this is going to be the maximum number of words that we're going to remember. And I'm going to set this to 2000. So then what I'm going to do is call encoder.adapt. And here I'm going to pass in our train data. And then actually, because our train data doesn't really, this encoder would only need the sentences, we're just going to also pass in a quick little lambda function because our train data is composed of the text and the label, but we don't really care about the label. We just want the text. So let's run this. Okay, and let's check out our vocab. So we can call encoder.getVocabulary. And then let's actually, let's take a look at this. Let's see the first 20 items. All right, so here these are words that are encoded in our encoder or part of the vocabulary. And this here, this represents any unknown tokens. Okay, then we can create our model. And again, it doesn't really matter which way you define it, but this is how I'm going to define it this time. And the first thing that we're going to pass in is the encoder, because the encoder is what is going to basically vectorize our text. And then we need to have some sort of embedding for this vectorized text. And that we are going to call keras.layer.embedding. So for the embedding, we're going to need to pass in an input dimension, and I'm going to set this equal to the length of the encoder's vocabulary. And then we also need to pass in an output dimension. So this output dimension, I'm just going to set equal to 32 because I think that's how many LSTM, that will be the size of our LSTM. And then I will also set mask 0 equal to true. And the reason why we use this masking is so that we can handle variable sequence lengths. Okay, so that's our embedding layer. So basically this turns these two together, we'll be able to turn our sentence into a vector of numbers that our neural net will be able to comprehend. Then next I'm going to add in a LSTM layer, and it's literally as easy as this. And we just, how many nodes there are. I put the output dimension as 32, so that's the value that I'm going to pass here. And then let's just add a dense layer. Let's do a dropout layer because, we saw previously that we might be prone to overtraining. And then finally, we result with a dense layer. Sorry, I totally typed these wrong. Dropout, and then dense 1. I also forgot the activation. So here we want sigmoid because this is the output. And up here we want relay. Okay, so this is our model. And here I missed another S. Cool. All right, now for the compilation, let's just borrow this right here. And again, we want to evaluate this on our train data as well as our validation data, just to see, what happens. So let's take a look at that. Okay, so our accuracy seems to be around 53%, not great. Our loss around 0.7. Okay, so now let's train our model. Let's try 5 to see what happens. Well, I will see you guys in a bit. All right, so now we're nearing the end of the training, and let's just take a quick look at the results. So here, our loss for our training data is decreasing strictly, and our accuracy seems to be strictly increasing. Now, let's talk about the validation loss. So it does seem like, we cut it off early enough that this is still decreasing and wavers a little bit. And our validation accuracy seems to be, the overall trend seems to be improving. Okay, so we have 84% accuracy here, which is pretty good. And finally, at the end, of course, we can evaluate our model once again. So here, it's called model.evaluate and use our test data to see what happens. All right, cool. So we get an accuracy on our test data of 84%, which is pretty sweet. That is the end of the Jupyter Notebook tutorial. And thank you guys, for being here, for following along with this. And now you've learned how to, not only implement a feed-forward neural network with numerical data, but you've also learned to use TensorFlow with text classification and trying to figure out whether or not a wine review based on the review itself is maybe, lower tier or higher tier, which is awesome. I hope you guys enjoyed this tutorial and, give this video a thumbs up if you liked it, leave a comment, and don't forget to subscribe to FreeCodeCamp and Kylie Ying. All right, see you guys next time.